So we are recording. So thank you guys for joining. Thank you for the Lebanon students that are joining tonight. Thank you for the Avon students that are here. And then we might have some students from a couple other schools like Franklin Central possibly, or Madison down south, and maybe any other schools. That would be perfect. So for my students, you obviously know who I am, but if you are from one of those other schools, my name is Brian Passwater. I teach at Lebanon High School, which is about halfway between Indianapolis and Purdue University in West Lafayette on 65. We've been hosting these webinars. This is our third one of the week. We did one on Tuesday and Wednesday. Tony Record at Avon did a session on differential equations. Then he did another session on those FRQs that have tables in them, Riemann sum, those types of problems. And then we're doing particle motion tonight. And then tomorrow, or not tomorrow, but next week, Tuesday, Wednesday, Thursday, again, the same 3 days, you might have noticed the PowerPoint that was kind of scrolling through for our upcoming sessions. The next week, we're going to have some sessions on rate in, rate out problems. We're going to have a session on area volume, and we're going to have a session on those miscellaneous topics that you see a lot of, that they're not always like a whole FRQ, but it'll be some things that pop up a lot on FRQs and how to deal with those. And Tony Record will be doing that one next Thursday. So tonight's all about particle motion. You know, if you're from Lebanon High School, hopefully you either downloaded this file so you can work it out on the actual document if you printed it off at home. If not, you can do it on your own paper, but make sure that you have all the problems completed and the notes that we discuss written down so you can turn them in to me tomorrow or whenever I see you next. We do have a moderator, so Mr. Record from Avon is gracious enough to be on here as well. And so he's going to kind of moderate some things. So if you have any questions, there's that chat feature that you'll have on your screen. You can type some questions in there, and he will either be able to answer your questions directly through the chat, or if it's more of a broad question or something that needs clarified, he will interrupt me to bring that question to the whole group. Or if he feels like the question you ask, there's probably more people that need to hear it, he'll kind of stop and interrupt and do that. So I'm looking forward to tonight, and hopefully you can bear with me through any glitches that we have. So we're going to jump right into it. So one of the things I love about particle motion is that it's on the AP exam every single year, and not every single year, but about 2 out of 3 years. So it's a very common topic, and it's one of those topics where we can really get a lot of free points, I think. The particle motion averages on the FRQs are not nearly as high as you might think they should be. And so students that are well versed in them are going to get easily 7, 8, or 9 points, whereas the national average might be anywhere from 2.5 to 4.5 points, right? And so anytime we can beat that national average, it's always a good thing. The more of a cushion, the more of extra points that you can kind of build up in your vault during the test, the better, because you're going to always have that one question that kind of blows your mind, or that one question that you just weren't thinking in the right way, you made a big mistake or something. And so this kind of saves you from those disastrous questions, right? So we're going to look at several FRQs on the particle motion, some of them that you may have actually seen. So they're not all going to be questions that are brand new. So you might have seen some of these, especially I know if you're at Lebanon, you've probably seen at least 2 of these, but we're going to see another one that I'm sure that none of you have seen because it's never been given on the AP exam before. So it's going to be unique to kind of put your knowledge to the test and give you kind of an idea of what kind of things they might ask on the AP exam. So the first one that we're going to look at here is the 2016 exam. This was AB number 2. And so since it was question number 2, we knew that calculators were allowed. And the STEM says for t greater than 0 or greater than or equal to 0, a particle moves along the x-axis the velocity of the particle at time t is given by this equation, v of t equals 1 plus 2 sine of t squared over 2. The particle is at position x equals 2 at time t equals 4. And so the first question that the AP exam kind of throws at us is this question of, at time 4, is the particle speeding up or slowing down? So I want to pause just for a second, because when we're doing the particle motion problems, you know, it's possible they could be a non-calculator problem. The AP exam is always interested in whether you can differentiate by hand and if you can integrate by hand, right? They want to know if you can do U substitution by hand, and not just on the multiple choice, but on the FRQs. So you know that somewhere on the AP exam, on one of the non-calculator questions, there's going to be an integration problem that involves U substitution, and there's going to be a derivative problem that involves chain rule. And so that problem could happen in many, many different contexts. It's very possible that that part of the test might happen during particle motion problem. So it's very possible that this question might be on the non-calculator portion, but they do tend, most years, you know, more often than not, you're going to see them on the calculator portion. So the first thing that we want to do when we're solving these calculator problems is make sure that we type the equation into our calculators, right? So the first thing we're going to do is get out our little calculator here and ensure that we can type in the equation correctly. So I'm going to share my TI graphing calculator screen. I know at Lebanon we always use the TI-84, but I know that at Avon, I'm assuming that most of you, if not all of you, probably use the Inspires. And I'm not sure at Franklin Central if you're more familiar with the 84s or the Inspires, but I'm going to be using the TI-84 graphing calculator emulator because that's all I know how to do. If you join Mr. Record sessions, he's like a calculator whiz. So he can use any calculator, the Inspire and the 84 or any of them. So if you're in his class, I'm assuming that you probably know how to input equations in there. If not, he can kind of help you on the chat. So when we go to the y equals, I was kind of prepared here, and I went ahead and put this equation into my y3 menu right here, 1 plus 2 sine of x squared over 2. So mine is in y3. So you might see me do some things in my menu using y3, but my assumption is you're probably going to have yours in the y1 menu. So be careful when you're kind of using the commands that you're using the command that you stored your equation into, and not just looking at the one that I did. So there's my equation. One side note, and we're going to see this more in a few minutes, but one of the equations from last year, there were so many students that typed the equation in wrong. And if they typed the equation in wrong, it literally cost them 6 points automatically, because every single answer in the problem was incorrect. And we didn't have any sort of mechanism or mercy for students who clearly typed the equation in wrong. If a student is in degree mode, for example, instead of radian mode, we're going to penalize them once, but then we kind of know what the answers would be if you were in degree mode. And so we only take off 1 point for that error, right? But if a student just types the wrong equation in their calculator, we don't have any compensation for that. And so you just miss every single one that involves an answer that's incorrect. And it was like a 6 point swing in the 2018 exam. So just make sure on a 3.5 hour test, you know, you're going to be tired and you're going to make mistakes that you would never normally make. So just take that extra 3 seconds after you type it in just to re-look at the actual equation on the AP exam and make sure that it's identical, right? And Mr. Record and I can say this through experience, because you would think to yourself, oh, I would never do that. I'd never made that mistake this whole year. And that might be true, but most likely you haven't taken an AP Calculus exam during an actual AP setting. You might have done a practice exam, but nothing like you're going to feel on May 14th exactly. So you're trying to prevent yourself from those little details that might cost you some points. So my equation's here in Y3. So with that said, I'm going to go back to my screen, and I'm hoping that I stalled long enough so that you could type yours into your screen if you're using your calculator. So the first question is at time 4, is the speed, or is the particle speeding up or slowing down? So before I write anything, if you were on Tony's webinar yesterday or on Tuesday, or if you have him in class, you know that Mr. Record's handwriting should probably be a font on Word. It's pretty much perfect handwriting. So I'm going to warn you right now, this is going to be a huge letdown for you. So I'm going to write the best I can, but I am not a human computer like Mr. Record is. So bear with me a little bit. So is the particle speeding up or slowing down? So I love this question because on particle motion, all the problems are incredibly scripted, meaning they ask the same things over and over again. And so if you kind of know like the 4 or 5 typical questions and what they're looking for, you're going to be able to get a whole bunch of points really, really quickly. And this is kind of a setup, because whenever it's talking about if the particle is speeding up or slowing down, we have to know the velocity and the acceleration both. It requires both of those values for us to make a decision about speeding up or slowing down. And so when they ask this question, the most common misconception, the most common error is that students think speeding up is acceleration. That if your acceleration is positive, you must be speeding up. And if your acceleration is negative, you must be slowing down, right? And that's a completely false pretense, right? Because you can be speeding up moving forward, and you can be speeding up in reverse. And so it's important to understand what exactly is velocity and what exactly is acceleration, right? And so just to break it down, both of these essentially are directions. The velocity is a direction. Your velocity is the direction of motion, right? The velocity always tells you whether you're moving to the right or whether you're moving to the left. It's a direction of motion. Which way are you actually moving, right? Acceleration is also a direction. And I'm going to use this phrase and I'll clarify it, but acceleration is the direction of, I'm going to put in quotes here, a push. So an acceleration on its own is not speeding up or slowing down. It's as if someone's pushing you, and it's the direction of the push. And so if you have a positive velocity, you know, if we're on the x-axis like we are here, we're talking about the x-axis. If you're on the x-axis and someone and your velocity is positive, it simply means that you're moving to the right. It's the direction. A positive velocity means you're moving toward the positive numbers. If your velocity is negative, then your direction of motion is left. You're going left. Acceleration is it's as if somebody was pushing you along that line. So if you have a positive acceleration, it doesn't mean you're speeding up. It means someone is pushing you toward the positive numbers. That's the direction of the push. And if you have a negative acceleration, then someone is pushing you essentially toward the negative numbers. So if we get to this idea of when are you speeding up and when are you slowing down, it takes both of these things. Because if you're moving toward the negatives, right? Imagine you're on this number line, right? And you're moving left toward the negatives. Well, your velocity is negative in this case because you're moving left. But if somebody pushes you toward the positives, this would be an example where V is negative. And if someone's pushing you toward the right, that's where the push is, your acceleration is positive, because acceleration is simply which direction am I pushing you, right? So if you're pushing someone toward the positives, you're going to have a positive acceleration. And you can imagine if you're trying to move left, if that's where you're walking, and someone's trying to push you in the other direction, you're going to slow down, right? So even though your velocity or your acceleration is positive, you're still slowing down because you're trying to go in one direction, but someone's trying to make you go the other direction, right? And so when we're answering questions about speeding up or slowing down, immediately you want to find V of t and A of t both at the particular time that's in question, right? So when I see at time 4, the first thing that we do is we say, well, we need to find V of 4 and we need to find A of 4. If we can find those two things, we can figure out which way we're moving as well as which way we're pushing, and that'll help us decide whether we're speeding up or slowing down. So going back to our calculators, thankfully I have V right here stored in Y3. So going back to my main screen, I just need to figure out what V of 4 is and what A of 4 is. So since I have V already stored in my Y3 menu, we have these nice shortcuts, right? The alpha keys are our shortcuts for F1, F2, F3, F4. So F4, right above the trace key, is where we have some shortcuts for all of our menus that we've typed in, all of our equations. If we go down to Y3, then when I make a parenthesis and put a 4 here, this is going to quite literally evaluate this is going to evaluate for us exactly what V of 4 is. And I just realized as I was doing that, I was still showing my AP problem and not my calculator. So this is my Y of 3 equals 4. So it's about 2.9787. And then I also need to find A of 4, and A of 4 is the derivative of velocity. So in our math menu, if we hit math 8, that's where our derivative is. We're going to take the derivative of Y3, right? So we go to our alpha F4 for our shortcuts, and we've got Y3 there, and at X equals 4. One of the things for time-wise tonight, I'm going to go a little bit more quickly through the calculator steps for two reasons. Number one, I know that many of you use the Inspire, and so me showing you all the buttons is going to be helpful to you. And then most of you probably are pretty comfortable on the keystrokes, but do me a favor, if you're at a school and maybe you haven't felt as comfortable with the TI-84s, or even if you're at one of our schools, like at Lebanon or even Avon, if you use the 84 and you've forgotten how to do something, jump on that chat and send a quick note to either the whole group or to the moderator, Tony Record, and just say, hey, can you remind me how to do this, right? And Tony can either tell you directly or he can reach out to me and tell me, hey, Brian, why don't you go show us how to do those steps? That way, everybody's on the same page. So we take the derivative of our velocity equation at 4, and I get negative 1.6400, right? So going back to our main screen, we're going to now write those down for the AP exam. If I can bring this back here. Perfect. Maybe, here we go. So I think our V of 4 was about 2.9787. There's a decimal point there. And our A of 4 was negative 1.16400-ish. And notice our velocity is positive and our acceleration is negative. So what's happening here is they're essentially working against each other, right? And so the shortcut, like what do you memorize to write down? If your velocity and acceleration have the same sign, they're either both positive or both negative, you're going to be speeding up. And if they have conflicting signs, if one of them is positive and the other one is negative, doesn't matter which one is which, then you're going to be slowing down, right? Like that's kind of like what you memorize for the exam. But it's also helpful to think about the motion, because when you understand why that's the rule, if you happen to blank out on the test, you can kind of piece it back together by some logic, right? When you understand why that rule is. So if they ever have the same sign, then we know that they're speeding up. If they're both positive, it means we're moving to the right. That's our direction of motion. And we're also pushing toward the right. So if you're moving in a direction and I push you that same way, you're clearly going to speed up, right? And if they are both negative, if you're moving left, a negative velocity, and I have a negative acceleration, it means I'm pushing you toward the left, then you're still going to speed up. You can speed up toward the negatives. It's like putting your car in reverse. You're going backwards. And if you slam on the gas pedal, it's pushing you back as well. And so you're speeding up in that negative direction. So in this case, they have opposite signs. So we're going to answer the question by saying slowing down, right? Slowing down. And our reason is very simple. It's because V of 4 is greater than 0 and A of 4 is less than 0. there's a lot of ways you can get that across. And so if your teacher did it a different way, then I guarantee you he's saying it correctly. So if you just said, oh, mention that V of 4 and A of 4 have opposite signs, that's fine. So there's a lot of ways to get that across. So don't just bank on this is how you have to do it, right? What is important, though, is when you write that down, be careful that you don't say V of T and A of T, right? Because we don't know if they always have opposite signs. We only know it's true at the time for. So I think it's simplest to just say V of 4 and A of 4. You could use V of T and A of T, something along the lines of V of T is greater than 0 and A of T is less than 0 if you say at T equals 4, right? But it's important that we know it's at time 4. With the new redesign, one of the new things they've changed in the last couple of years is the College Board is really holding students more accountable for what you put on paper. And so you have to be really careful that you don't say things that are false, right? You might have meant to say 4, but if you don't mention that 4, there's a chance that they could come back and deduct points, right? So this is all we have to write. Notice it didn't even say on the test, give a reason for your answer. It's just expected when you talk about speeding up or slowing down that you kind of give them a reason, okay? So those are pretty standard problems. So let's move ahead a little bit to part B, and we'll look at part A and B, and then we'll kind of look at the scoring guide once we have that written down. So in part B, find all the times when the particle changes direction. So one of the things that you want to do on the AP exam is get really good at translating words into mathematical equations or mathematical inequalities, right? So you want to kind of get this approach of when I see this phrase, this is kind of the mathematics behind it, right? And so if a particle changes directions, you can't change directions unless your velocity changes signs, right? This is what we're looking at, is there has to be a change in sign of velocity, which means in order for velocity to change signs, we also need velocity to be 0 first, right? You can't change directions unless you stop, at least momentarily. And so to change directions mean velocity change from either positive to negative or from negative to positive. And some key phrases here is talking about direction, right? Remember, we already mentioned the direction of your motion is based off of velocity. So this phrase, I know, should have something to do with velocity. And so what I like to do is when I see a phrase like this, notice it says justify your answer. I like to actually justify my answer before I even find an answer. I think one of the mistakes that students make on the AP exam is they read a question and they just start typing buttons on their calculator. You start graphing stuff or typing equations in, and you haven't really thought through what the path to the solution is. You know, if you've done a bunch of problems where you start with position and you're always used to saying, oh, on these problems, we always took the derivative. Well, that's because you started with the position equation. You know, if you start with velocity, you're not going to take a derivative, right? And so it's helpful, I think, to translate these problems first before you start thinking about which equation to use and how you're going to use that equation. And so if a particle changes directions, I'm going to say the reason is because V of t changes sign. That's what would create a change in direction. And I might even put, for my own sake, check when V of t equals 0 first. But as soon as I write this down, this tells me I need to look at a graph of V of t. So then I can double check and say, well, which graph did they give me in the problem? Did they give me V of t? Did they give me, which equation did they give me? So we're going to look at the graph of V of t, and notice the window here is just between 0 and 3. So when we go back to our graphing calculator, I'm going to go back to my window, and I'm going to change my x-min to 0. Always change the window to be the window that they gave you in the problem, and my x-max to 3. And then the y-min and y-max is a little bit debatable about what maybe you should, what window you should have. But whenever I want to figure out when something is 0, I don't like to make these very big. So I like to kind of start with -5 to 5. You could do it from -3 to 3 or from -1 to 1. Any of those is fine, but you don't want to go up like 100, because then you may not be able to see the graph very clearly. So this is a graph of velocity, right? Because we had that stored, I believe. And I just realized something. You don't know this because you only have one thing typed in your equation. I've got all three of these typed in my equation. So if you were looking at yours thinking, what's going on? I'm graphing all the other problems that we're going to see later on. So this is just my graph of velocity now. So here's our velocity graph from 0 to 3. And notice we're trying to figure out when v of t changes direction. This is, or when the particle changes direction, I apologize. So this is a graph of v. So we're just trying to find out when v changes sign, right? And we can see it's right here. This is the only place where velocity is 0. And before this point, velocity is positive, and after this point, velocity is negative. So I want to find out what that point is. Whenever you have a graph and you want to find a point, we always go to this calculate button, right? The calculate above the trace key is how we find points. I just need to figure out that 0 where this graph crosses the x-axis. And it's going to ask us for a left bound and a right bound if you're using the 84. So for the left bound, just put the cursor anywhere to the left, doesn't really matter where. And then we're going to move it a little bit past that point. When it says right bound, we're going to go toward the right of that point and hit enter again. Then it always has this guess here because it's asking if you have a guess, but we just hit enter. And it should move the cursor. You always know you've done it correctly if the cursor jumps to the point, and notice our y coordinate here is 0, which makes sense. Because of the accuracies on the calculator, every once in a while for your y coordinate, you might see something weird like 1.072 e negative 8 or something like that. And you're like, well, why does that have this number there? If it starts going into scientific notation, it literally is 0. It's 1 point something times 10 to the negative 8th or whatever. Because there's pixelations in the screen, sometimes it doesn't find the exact 0. It finds a really, really close answer, but I promise you that your answer is correct. So here we're looking at 2.707468. So we can go back to our point and say t equals 2.707468. And I'm sure that Mr. Record mentioned this the other day, but on the AP exam, we're only reading the first 3 decimal points, and you can round them or you can truncate them. But in my classes, you guys know I make you write them all down because sometimes you have to use these numbers again later, and this is going to allow us to be accurate for later approximations, and you never have to worry about whether you have enough numbers or not if you just write them all down. It takes you not even 1 more second to write all the numbers down. So I just write them all down every time. And then the nice thing is we already have our justification, right? When it says justify your answer, make sure you realize there is not a single problem on the calc exam that will require you to write more than 1 sentence. Every explanation, every reason, every justification, if you know it well enough, there's a 1 sentence acceptable answer, right? We're trying to be short and sweet with our answers. We're not trying to linger and repeat ourselves. And so here, if you want to, we can go ahead and rewrite it, but it's perfectly acceptable to write your justification or your reason before your answer. And I actually like that strategy because if you write your reason first, then that tells you what to go look for on the calculator, right? It's giving you a map of what to find, so that way you kind of know what you're looking for before you get your answer. So this is our reason. Make sure that you don't say because v of t equals 0. Just because your velocity is 0, that does not indicate that you're going to be changing directions. It just means that you're stopped, right? Just because you stopped doesn't mean you've changed directions. So what I want to do is I want to jump to the scoring guide really quickly, briefly, just to kind of show you how this is going to be scored on the exam. And that is not the correct one, but this is it right here. And so notice on this problem, I'm just going to show you A and B. Part A was worth 2 points. And it was 1 point, it there were 2 points basically for the conclusion and the reason. So having the values of V and A, and then also mentioning the answer and the reason, that combined gave us 2 points. And then in part B, 1 point for the answer that we got, and then 1 point for our justification. This says V changes from positive to negative. You don't have to say that it changes from positive to negative for velocity. You can just say that it changes signs. If you want to include the positive to negative, you can, but then sometimes students will get it backwards. So if you say it wrong, you're going to end up losing that point. So V of t change of signs is a universally accepted answer. So this is 4 points already in part A and B. And not to get ahead of ourselves, but just so you know, the national average on this entire problem was only 3 points. It was a 3.0 average. So the first 2 parts were pretty straightforward, and you're already beating the national average, right? Which is great, because anytime you're getting the national average on a problem, it means you're kind of getting approximately, you're kind of getting a 3 on the exam. The national AP average overall for the AP test is about a 3. It's like a 2.9 for the AP exam. And so when you see those average scores, that's what a student who would get a 3 on the exam typically would score. So anytime you're beating the averages, it means you're getting a 3 or better on your pacing for that, right? So if you did it on all the problems, it would kind of tell you how you're pacing on the exam. If your goal is to get a 4 on the AP exam, your goal should be to beat every FRQ by a point. If you can beat every average score by a point, then you're kind of pacing for a 4. And if you can beat every average score by 2 points, now you're in that 5 range of tracking for a 5 on the AP exam. So the rest of this problem, part C says find the position, right? And we have a very standard formula for position. And I want to start with going back to this, because I know that a lot of my own students will mix this up sometimes. You're so used to, when you write an ordered pair, you're so used to making it x comma y all the time. So you're kind of in this habit of x always comes first. But when we're doing particle motion on the x-axis, we don't have a y coordinate. We have a t and we have an x. So anything with motion, t always becomes the x coordinate. And then the position, doesn't matter if it's x or y, that becomes the second coordinate. So when you see position 2 at time 4, I think it's helpful to write that as an ordered pair now, because it'll save you some trouble later. This is the point 4, 2. And you can already see how if you're going too quick or not paying attention, it'd be very easy to write this as 2, 4, because they gave you the x values and you're so used to putting that first, and they put the 2 before the 4, right? And so it's easy to kind of mix those up, but t is always going to come first, right, in our problem. And so we're trying to find the position at time 0. This is the fundamental theorem, right? Anytime that you want to know the value of something, it's always equal to a starting value, some value that you know or that the problem gave you, somewhere to begin, plus the integral of the rate or the derivative. This is used in so many ways on the AP exam. It's used with particle motion. It's used with, those graph problems of f prime graphs that we'll see next week. It's used with, like you take a pizza out of an oven and you want to know what the temperature is after so much time. All those kind of problems that are asking you for an amount or a value utilize this modified form of the fundamental theorem. So in this case, we want to find the position at 0. That would be x of 0. It's always going to be equal to a starting place. Well, remember, they told us x of 4, right? When you see 4, 2, that means x of 4 at time 4, the x value equals 2. So the position they gave us was x of 4 plus the integral of the rate. In this case, the derivative of position is velocity, right? V of t. And then I purposely left the limits off for a moment, because whenever you're doing this formula, we're so much in the habit of putting 0 and 4, and we want to instinctively put the 0 on bottom and the 4 on top, because that's the proper integral, right? But we don't really have a choice. When you're doing the fundamental theorem, we always put the starting time goes on the bottom, and the time that you want to find goes on top. And so our position at time 0 is going to be x of 4 plus the integral from 4 to 0 of v of t dt. And then this is why I make my students write x of 4 here and not just put a 2 there to begin with. We know the position, the starting position is 2, but sometimes when you put a 2 there, it's just enough to kind of make you make a mistake on those limits. So I always start with this, and then I'm going to rewrite it one more time to say x of 4, I know that's 2, right? So I can replace that with the 2. We want to always have numerical values before we type things into our calculators. 2 plus the integral from 4 to 0 of v of t. And because it's a calculator problem, we can just type this directly into our calculators, right? So if we go back to our calculator here, I'm going to go and open this back up and go back to my main menu. And we're trying to go back to what was the equation. It was 2 plus, and then to integrate, remember that's math 9, or if you're using the Inspire, I'm sure it's something. I'll let Mr. Record deal with that. From 4 to 0 of the velocity, and remember our velocity equation I have for mine, that's in y3, but you're going to choose whatever equation you put it in. And that's going to go from 4 to 0 of y3 in my case dx. So this is kind of what we're dealing with right now. If we hit enter and we wait for a somewhat long time, we get our answer of negative 3.8152684. And we can type this now into our answer. So our final answer is going to be negative 3.8150268. And that's it. That's the position. And then finally, in part D, it says find the total distance that the particle travels from 0 to 3. So they're giving us an interval. And then this key phrase here is total distance, right? As soon as you see that phrase total distance, we have a straightforward formula for that. The total distance of a particle is simply the integral of the absolute value of velocity. It's not the integral of velocity, it's the absolute value, right? Total distance is the integral of the absolute value of velocity from something to something, right? And then if you were to integrate just the velocity without absolute values, that's what we would call the displacement, right? The displacement is a very different idea, and if you're in physics, I'm sure you're very comfortable with that idea. But the absolute value is sort of like what your Fitbit would measure during the day, or your phone, if it's measuring your distance walked, right? It's measuring all the total distances that you walked, whereas displacement basically says, where did you start? Where were you when you first began? And then where were you at the end? I don't care what path you took. I just want to know how far were you from when you first started, right? And so if you think about a number line, if you started right here at 0 and you're walking kind of like backwards and forwards or whatever, and you end up stopping at 3, well, your total distance is going to be much bigger than 3. You're walking past it, then you're coming back and back and back. You've got a pretty long total distance, but your displacement is merely 3 because you started at 0, you stopped at 3. So regardless of what you did in between, you're only 3 away from where you began. So this is going to be a little bit different than total distance. So the AP exam loves those total distance questions. And so it's going to be the integral of the absolute value of t. And they even were kind enough to give us these limits from 0 to 3. And so now we can just type this into our calculator again. So if we go back to our graphing calculators, and we're going to go now to Math 9, another integration problem from 0 to 3. And we're trying to graph the absolute value of velocity. And so there's a couple of ways that you can get to those absolute value signs. I like to look down here under catalog, this little blue button above the 0. If I hit the blue second and then I hit catalog, the very first option is absolute value. That's why I like to use this one, because I know it's the first thing that pops up. ABS means absolute value. And when you hit it, if you have the TI color like we do at Lebanon, or if you have the 84 and it's updated, it'll actually make the nice absolute value symbols for you. And then we're integrating the velocity, right? The absolute value of velocity. So we're going to put our y equation in there. I put y3 again, but yours might be a little bit different, of dx. And we get a total distance from 0 to 3 becomes, I think the anticipation is killing me. I hope my calculator, oh man, my calculator had a hard time with that one. I think because maybe I'm running a few applications. I'm assuming that if you were doing that on your own personal calculator, it probably would have calculated that much quicker than mine did. So this is going to be 5.301. So now we can just type this straight into our calculator and say this is going to be 5.301204428. I caught a little bit of Mr. Record's webinar yesterday. He talked a lot about equal signs versus approximation signs. These are probably, whenever I'm giving my answer, they're all technically approximation signs. I put equal signs. Luckily, the College Board doesn't grade you on whether you use an equal sign or an approximation sign, mainly because of people like me, where it's too hard to read their handwriting. It's too hard to decide what they did, right? So, but technically, those probably are going to be approximation symbols because we're rounding our answers a little bit. So going back to the scoring guide for part C and D, if we scroll down a little bit, notice part C was worth 3 points. 1 point for knowing to integrate the velocity, right? To know that we had to integrate velocity from 4 to 0, that idea was worth a point. And then knowing that to find your position, you have to have a starting position. That's the condition. That's a point. And then your final answer of basically number crunching correctly on the calculator and getting the proper answer was a 3rd point. Those are 3 pretty easy points on the exam. If you know that formula, you're going to get those points every single time. And the same thing in part D. The total distance is just the integral of the absolute value of velocity. Notice 1 point for the integral. So the absolute values are really important. You had to have those written down. And then when it says integral, you have to have the limits correct as well, 0 to 3. So that was worth 1 point. And then 1 point for number crunching on your calculator and getting 5.301. I want to make one quick note about you know, these rubrics. It's really important when you're using your calculator that you tell the reader, you tell Tony and you tell me what you're doing, right? I know you can probably type this all into your calculator, but if you don't have this set up, if you don't tell us, I know to type this thing into my calculator, and you only have the answer, the odds are you're going to get 0 out of 2. If you don't show the setup, we call that a bald answer, an answer by itself with no proper work, and we're pretty much not even going to give you the answer point. We're going to give you absolutely nothing, right? I always say give them the answer point, but Tony always votes against it. He's always like, no, I want to punish these kids as much as possible because he's just like that. I don't know. I try to talk him out of it, but he is who he is at this point. Oh, I forgot that Tony is allowed to make comments in the chat. Might be. So I'm going to jump ahead a little bit here. So if you have the packet, I'm going to skip this next one. This is another one that's very similar to what we just did from 2013, but I wanted to show you how they're all kind of similar in nature. And so if you have time and you want some more practice, you can definitely do that one, and you're going to realize it looks a lot like what we just did. So it's a neat one to look at. But I want to point out a couple of pieces on some other ones. And so this is one that I'm certain that you have not seen before because I wrote it and it's not on the AP exam. And I wanted to talk about it for a few reasons because it ties in a lot to what Tony did last night, right? If you didn't watch it last night, you can get the recorded session, but he did a whole session on working with tables like this. And so it's very possible that the table could be an absolute or a velocity graph, right? You could do particle motion with equations, but you could also do particle motion with tables or even possibly with pictures of graphs, right? And so it's important when you learn these ideas that you don't just think, oh, I can type numbers on my calculator, but I understand the formulas well enough that I could do them in other ways as well. So this is a table of time, various times, and of velocity. And Stephen is skateboarding along a straight road, and this is his velocity in meters per second, and it's continuous and differentiable, and it's given for different times in the table. So the first question is approximate Stephen's acceleration. And so it's asking us to approximate his acceleration. Well, we're given velocity in the problem. So acceleration is the derivative of velocity, right? So if we had an equation like we did in the last problem, when it was asking for acceleration, we could just take the derivative because acceleration is the derivative. Well, when we have a table, we're not able to take a derivative because we don't have all of the information. When we have tables, we start having to approximate or estimate things. And so the best way to estimate or to approximate a derivative is using slope or rate of change. So at t equals 4, it's right around here, right, between 3 and 7. So to approximate his acceleration, we're just going to find the slope between the 2 points that are closest to 4. It's really important that you pick the 2 points that are closest. You don't get credit if you pick other points. And I always thought that was interesting because technically it is an approximation, but when they say approximate, they want the best reasonable approximation. So in this case, we would say 0 minus 3, remember y2 minus y1, over 7 minus 3, x2 minus x1. And then we don't need to simplify this, so I'm going to leave it like this. We can leave things with numbers. And then it says include units of measure. I always think this is the point that sometimes students miss for no reason, and I think it's because you overthink it. When you're doing a difference quotient like we did and you want the units, think about the 0 and the 3. Those two numbers, the units for that were meters per second, right? So if you put the units right next to those numbers, and then over, 7 minus 3 is also in seconds, all right, over seconds. What I have right here is completely acceptable to leave as your final answer. Remember, you don't have to reduce any numbers, and when you have units, you can leave it like this. Some of you want to make this meters per second squared, which is completely acceptable, and you're allowed to do that. I would prefer almost for my students to not reduce this, because on a long test, I don't want them making a weird mistake and thinking these S's are going to cancel for some reason because they're not. And so I like to just leave it like this and then move on. And then part B, this is where I want to mention is use a trapezoidal sum with the 4 subintervals indicated in the table to approximate this. And this is something that was definitely in the webinar last night, where trapezoids and Riemann sums. And so if you are a little bit shaky on some of that, definitely go back and rewatch that webinar. It was a really good webinar. I was able to hop on for most of it. And so looking at this table here, what I do in my class, this might be totally different than what you do, and don't worry about that. I have my students make a quick fake graph of V. And I say, don't even try to make it match the table. We're just doing this so we know how to pick the right numbers out of a table. When you make a little picture on the AP exam, we're not really using that you know, in our grading, right? We're just knowing that you're probably doing that to organize your thoughts. So I like to take all the X values, 1, 3, 7, 8, and 9, or 10 in this problem. Those are the X values in the table. And I do that because if I just draw lines up, I can immediately see that we have 4 little spaces here, which is why it says 4 subintervals. And then I have my students label the height of each one. And so it's -2, 3, 0. So -2, 3 is the next one, 0. And then I think it was -4, and I'm hoping it was 7. Otherwise, I'm going to have to erase that. It was 7. That was awesome. These were the different Y values for each of those. And the reason why I do this is because when you're doing left Riemann sums or right Riemann sums, you might never make a mistake and you're fine. But I'm a visual person, and when I pull numbers out of tables, sometimes I make a little mistake. So this is kind of just there so that way we can't possibly make a mistake, because I can see which side of the rectangles they're on. So the trapezoidal sum, we know that the integral from 1 to 10 of the absolute value of v of t dt is going to be approximately, and we're just going to do the trapezoids. We know every trapezoid has a 1/2, right, in front of it. The area of a trapezoid is 1/2 HB1 plus B2. And when we do trapezoids in the AP exam, remember the bases are actually going vertically because those are the parallel sides, and the heights are these bases down here. And think about these bases. The first one is from 1 to 3, so that's going to give us a base of 2, or a height of 2, I guess, in this case. And then from 3 to 7 gives us a height of 4. From 7 to 8 is a height of 1. And from 8 to 10 is another height of 2. And so when I have these numbers, we can use our formula really pretty quickly. So for the first trapezoid, the height is 2. And then we do base 1 plus base 2. And this is where students, this exact kind of problem was on the AP exam a few years ago, and a lot of students missed it. And here's why. Because we're not integrating V, are we? We're integrating the absolute value of V. So we're actually making all of our velocities positive before we add them up, right? The integration sign adds them all up. This is saying make everything positive before you start adding. And so all of these numbers technically should be absolute values here, right? And so this -2 for adding the absolute values becomes a 2 in our problem if I'm doing the absolute value versions, and the -4 also becomes a 4. And so when I'm writing these out, I know the formula now is going to be the height, which is 2, and then base 1 plus base 2 is 2 plus 3, right? And not -2. And the next one, the height is 4 for that second trapezoid, and our two bases are 3 and 0. And then the third trapezoid, the height is 1, and we're going to have 0 and 4 for our two bases. And then finally, our last trapezoid has a height of 2, and then the bases are 4 and 7. And as soon as we have all this information, we can leave it just like this, right? There's no requirement or no need to add those up and simplify, especially because this is a non-calculator problem. You're not going to get any benefit from doing that. And then the last part of this is what I know a lot of my students, and even I have this problem sometimes, you get so such a feeling of accomplishment when you work out the problem, you're ready to move on to the next question, but be careful for the multiple sentence question, right? When they have multiple sentences in a problem, they're probably asking you to do multiple things. So don't just answer the first one and then move along. Make sure you read the whole question, right? RTQ, ATQ, read the whole question and then answer the whole question, right? So make sure that you read the question, answer the question. So the last part says, using correct units, interpret this value, right? And so what did we do? We integrated the absolute value of velocity. We mentioned that on the last example. This, right? This integral from 1 to 10 of the absolute value of velocity is the total distance, right? The integral of an absolute value is a total distance that, and what was our person was Steven, was it? It was that Steven skateboards. And then we always have to include our units. So think about if you integrate velocity, velocity was in this particular problem, velocity was in meters per second. When we integrate that, we're going up to like distance, right? If you're asking how far did you travel, that would be in meters. So it would be in meters, always include the units. And then we always need to include the interval as well. So we can say over the interval. And a lot of students I notice do a lot of good interpretations, but they don't give the interval. Anytime you have an integral, you have to mention that it goes from 1 to 10 seconds. So the absolute value, the integral of the absolute value of velocity is the total distance that Steven skateboards in meters. We have to have our units there, right? Over the interval 1 to 10 seconds. We need all of those pieces to get all of those points, right? So I just wanted to show you that brief question, and I'll leave the second part of that question to you. There's a couple more problems there. And again, if you don't have this file, I put it on my Canvas. I know that Mr. Record put it on his Schoology. If you are out of school that's not Avon or that's not Lebanon, tell your teacher to email us and we will send you the problems from tonight. That way you can have them and finish them. But I'm going to let you try those last two on your own, because I know that no one has done those before. And I want to mention a few more things here. We're almost done for the evening, so thank you for being on and hopefully gaining some insights and hopefully feeling a little bit better about particle motion, because there's a good chance it's going to be on the exam and it's a great problem for us to see if it is. I want to go to the one from last year because I have a feeling that a lot of my own students lost a couple of easy points here, and it was because of me. And so this is with the redesign. And so this says a particle moves along the x-axis. That sounds familiar, right? And they gave us this velocity equation, and they gave us an interval, and they tell us the position at -5, the position is -5 at time 0, right? That means that x of 0, when t is 0, is -5, right? That's our starting position. And it says that find the acceleration of the particle at time 3. Well, we know that if we have velocity, all we have to do is take the derivative, right? And we have a calculator, so we're not going to do it by hand. We're just going to use the calculator. But what a lot of my students did last year was they just wrote, oh, once the acceleration, I'm just going to say the acceleration equals a number. And this was only worth 1 point, part A was. If you just wrote acceleration equals the answer, you did not earn that point. And the reason why is because you didn't communicate how you found acceleration, right? You and I know that acceleration is the velocity, or is the derivative of velocity. So you have to tell on the AP exam that you know that. And so what we should do is either in the problem say v prime, v's derivative equals a. We're making that connection. By the way, this idea of connecting this is going to play a huge role next week when we talk about f prime graph. This is going to come up in a major way, making a connection between something's derivative and another function. Either write it out to the side, or we could say a of t equals v prime of t, or something like that. Or we could say v prime of 3 is equal to a of 3. But we're looking for some kind of connection that you knew to take v's derivative and didn't just write an answer down. That's kind of what they're looking for in that problem. So I want to show you my graphing calculator really quick one more time, because I have mine stored here in Y2. And this is the example that I was mentioning in the beginning of the webinar, that I could tell that so many students didn't use this fraction notation. They just wrote the numerator, and they just used the divided by sign, and they wrote the denominator down. And when they did that, they didn't put parentheses around the denominator. So your calculator didn't interpret it the way that you were thinking, right? It was using proper order of operations, and you were wanting it to divide by the whole quantity. And there were a ton of kids that lost the easiest points because of that on this whole problem. So I think it's so important that we use this fraction notation. If you're using the TI-84, when you hit the alpha key, that shortcut green alpha button, above the y equals where F1 is a shortcut for fractions. That n/d means it's going to create a nice, pretty fraction like we see here, that will make sure that you don't have any mistakes when you input things, right? This is another example where it's really helpful to, after you type it in, make sure that you get everything correct. So this is stored in Y2. So I want to find the derivative of my Y2 function. Yours might be a little bit different if you typed yours in a different space, right? And I want to find the derivative at what value? Is it at 3, I hope? We'll find out. If I hit at 3, I'm now starting to think that is what they wanted, right? So let me find this again. So at 3, our value, it's thinking about it. My screen is now all of a sudden acting a little bit wonky here. I'm going to go back to my regular screen, and maybe my calculator will show up then. There we go. So the derivative at 3 is 0.032119. 0.032119. So that's going to be 0.032119. For some reason, that really feels off to me. I want to check my scoring guide because I'm almost wondering if I somehow managed to type that into my calculator wrong. And that definitely is wrong. I graded this problem last year. So I'm going to go back to my calculator, and I did that on purpose just to give you an idea of how you can type something in wrong, right? Actually, I didn't. I'm just an idiot. But I'm going to double check here on my equation. My y2 is 10 times sine of 0.04x squared. And that looks correct. Oh, I already figured out my mistake. The equation in the problem was 0.4. It was 0.4, and I had typed 0.04. So this is actually what it should have been, right? 0.4x squared. So if I go back, now that I fixed that, and I go back up to recalculate this derivative, it's not 0.032, it's going to be negative 2.118. So let's just pretend like I did that on purpose to teach you a lesson, all right? And then we'll just keep that between us. And then Tony, I'm going to need you to edit this or have some kind of technical glitch where it goes silent for a few minutes. That would be great. So in this case, ignore everything I wrote right there. And this is negative 2.118 is what we're looking for on that problem, right? So let me go back to my screen. And we'll magically pretend like this never happened right there. And this was going to be a of 3 equals a really long equal sign there. That's just how I did it. Equals that. So a couple things I just want to point out to you on this problem. Look at part B. It said find the position at time 3. We've talked about that already, right? That if I wanted to find the position at time 3, we could just simply do x of 3, right, equals a starting position. And in this case, our starting position was x of 0. That's what we had to begin with, plus the integral from 0 to 3 of the velocity, right? Just that same kind of formula that we've been talking about for a little bit is right back in there. And so, and then we know that x of 0 is negative 5, and then we're going to get plus the integral from 0 to 3 of v of t dt. And there's another easy few points right there. So if I kind of scroll back here to our scoring guides for 2018, notice part A was worth just 1 point, and then part B by itself was worth 3. 1 for the integral of velocity, 1 for remembering to add that negative 5, and then 1 for typing things in correctly into our calculators. It's so formulaic in that position that we just need to like practice getting those formulas memorized, right? So let me jump back here to our screen just to show you the very end of this problem. And I know that we're a few minutes over, so I promise you that we're not going to finish all of these, but just to kind of point out a couple things to you. Part C says evaluate the integral of velocity and evaluate the absolute value of velocity, the integral of that. Notice they did change the limits a little bit to 3.5 now. So those are just things that you would type into your calculator, and then you would just show them on the answer key. And then it says interpret the meaning of each of those. So we've already discussed this on this last problem, that this is the total distance the particle moved, right, from the interval 0 to 3.5. And this one is the displacement of the particle from 0 to 3.5. And so those are one of the things the exam really is hitting on this year is, in the last couple years, can you interpret a derivative and can you interpret an integral in context of a problem? I would pretty much make any bet that you want that you're going to have to explain what a derivative means on the FRQs, and you're going to have to explain one of your integrals on the FRQs in context. And so it's definitely worth practicing that phrasing so you're used to it. And then the very end of this problem says a second particle, now they introduce another particle, we'll call this x sub 2, Notice this equation is not the velocity, but it is the position, right? So the first equation they gave us was the velocity of some particle, and now they've given us the position of a particle, and they want to know when are they moving with the same velocity. And so if this is our x sub 2, the velocity of that particle, we're talking about velocity here, the velocity of this new particle is just the derivative, right? We have position, and then we have underneath that is the velocity, the derivative, and then that next derivative becomes the acceleration, right? And so if we have position and they're talking about velocity, we should differentiate this, and that's going to be 2t minus 1, right? Is that simple derivative. That's the velocity of the second particle, and we already were given the velocity of the first particle in the problem, and they want to know when those two particles have the same velocity. When does v of t, which is what they gave us in the problem, equal v sub 2 of t, right? Or when does that equal 2t minus 1? On the AP exam, whenever you find yourself having written down an equation, you're like, well, how am I going to solve this? Please don't try to solve it by hand if you have a calculator. Any equation that you ever have and you want to solve it, whether it's two different formulas or there's numbers involved, type one of them in your Y1 screen and type the other one in your Y2 screen and just see where those two graphs intersect, right? So you can always graph them separately, put one of them in Y1, the other one in Y2, and then graph them both and just look on your calculator to where they intersect. So I just want to show you the scoring guide, just so you can see kind of these points were awarded. We talked about how part A was worth 1 point and part B ended up being worth 3 points. And then part C, where they were finding the values, just literally typing them in on your calculator. That was literally testing if you knew how to find math 9 on your calculator, if you're using the 84, if you knew how to use absolute value signs as well. And you got 2 answers. Having both of those correct was worth a point. And then your 2 explanations were worth 2 points, 1 for each essentially, right? We won't get into the nuances of how those points are kind of awarded, but basically if you had one of them correct, you got 1 point. If both were correct, you got 2 points. And so you got 1 point for each of those for remembering that total distance uses absolute values and displacement does not. And then in part D, notice the first point is just for saying that the velocity of the first particle, v of t, is equal to the velocity of the second particle. And you could have written that like they did here, or you could have called it 2t minus 1 like we did, but just knowing that they're equal to each other is the first point. And then knowing how to type them into your calculator, putting one of them in Y1 and one of them in Y2 is going to be the second point. So this is going to be another kind of example where we can get a lot of points. The average on this problem actually was pretty high. It was 4.21. So it's still less than half of the points, but it's something that we can definitely beat. So do me a favor, really brush up on your particle motion. If you see this phrase, here's what this means, because most of it, it's about 90% memorization. And if you remember those things well and you practice some of these, and you get one on the exam, which I think there's about a pretty good chance you're going to see one, you're going to rack up a lot of points really quickly, and that's going to make a really, really big difference. So we were supposed to go 8 to 9. It's 9:13, so if you know me, that's pretty good for me not going over too long. So if there's any questions and you want to stay on and either ask some questions for the chat or you want to unmute yourself and ask a question, I'm happy to do that. But I want to thank you guys for coming on. Nothing is more exciting than a whole day of school and calculus and then jumping on to a webinar at 8 o'clock at night. So I'm really proud of you for jumping on here. The AP exam is in 12 days, right? You've got 12 days. So do me a favor, jump on as many webinars as you can, but more importantly, practice as much as you can. Get 1 point better. Commit yourselves right now to say, over the next 12 days, I'm going to work to get 1 point better every single day. Find 1 point, memorize one more formula, get better at one more thing each day. If you get 1 point better, you're going to be adding 12 points um, to your overall score. That's a huge difference. 12 points will raise you one number grade on the exam for sure. And there have been years that 12 points was the difference between a 2 on the AP exam and a 4. There are students that have gotten a 2 that were only 12 points away from getting a 4. So every single point matters. Little details matter. Take advantage of those things. And our next webinar is going to be next Tuesday, Tuesday night. Next Tuesday night, I'll be on again next Tuesday and Wednesday. And then Tony, Mr. Record, will be back next Thursday. So thank you guys so much for joining. Hope to see you guys again on Tuesday, Wednesday, and Thursday. And then the recorded sessions will be available to you. If you're not at Avon or Lebanon, ask your teachers to contact us and we'll get you all those files so that way you can watch them and then become awesome like us. Have a great night.